Hello, everyone. This is Dr.Hira, and this lecture we are going to talk about the Lewis structure and the formal charges. So this is basically the one of the basic or the core concept when we are talking about organic chemistry and how to draw the structure. But most of the students find this difficult that how they can draw the Lewis structure rightly, and what should be the formal charge of the molecule and individually on atoms. So that all we will discuss today. So firstly, before going into the detail that how we can draw the Lewis structure, this is important that you get familiar with the person who proposed that theory. So the chemist Gilbert and Lewis from 1875 to 1946. He introduced the theory of the electron pair. And we know that this electron pair theory is basically the basic principle and the found and it extend or understanding for the covalent bond and of the concept of acids and bases. And these acids and bases are the Lewis acids and the bases. So in his honor, that we often refer to an electron dot structure as a Lewis structure. So they both are the alternative terms. So you should not confuse with this one. So these you can say either the electron dot structure or the Lewis structure, but the Lewis structure is more famous, and that had extended in the honor of Gilbert and Lewis. One more thing is that the and Lewis was considered as the most influential American chemist, and he has contributed a lot in his life on the chemistry, on the scientific, and on the community service as well. So let's talk about the Lewis dot structure. Um, as you got familiar till now, that what are the condensed structure, what is the molecular formula, how we can draw the open structure, and how we can draw the line structure in any of the molecules when we're talking about the organic compound structure. So now this is a new term for you, that is a Lewis dot structure. A Lewis dot structure is a very simplified representation of the valence shell electrons in a molecule, and it is used to show how the electrons are arranged around individual atoms in a molecule. Electrons are shown as dots, or for bonding electrons as a line between the two atoms. The goal is to obtain the best electronic configuration, and that is basically the octet rule. We know that what is the motivation and what is the urge for an atom to make a bond. Either it is going to the ionic bond, either that is making a covalent bond. But as we are talking about organic chemistry, so we are more concerned about the covalent bonds, right? So the covalent bond, and we have talked about that every atom is in an urge to attain its neighborhood or its nearest analogous configuration, and that is that most of the atoms should acquire the 8 electrons in the outermost shell. Remember one thing, that here we are not concerned about the whole electronic configuration when we're talking about the valence shell. So we're concerned about the outermost shell. So that outermost shell should acquire 8 electrons to complete their octet, and that is called the octet rule. The hydrogen is the only exception because it's the simplest and the smallest element of the periodic table. So it needs to acquire, and it can accommodate only the 2 electrons in its outermost shell, and it is looking for the electronic configuration of the helium, which is just next to that which is the member of that same um, row it is sharing, right? So why we need to draw the Lewis dot structure, you may have seen some of the books where you have seen some of the formulas, and they are different than the normal open structures and the line structure. There you may have seen that there are the charges are mentioned, either the positive or the negative one. There are the electron pairs or the dots are mentioned. So these are basically for writing the right mechanism when we are talking about organic chemistry and what is the chemistry behind how the reaction proceeds, and the synthetic chemistry, what would be the nucleophile and what would be the electrophile. So for this, we should have the complete information that where this electron pair or the lone pair do exist, where it is located, what an atom is carrying as the as a charge, and what is the overall charge of a molecule. So then we can draw the right mechanism. So this is very important when you are writing and we are drawing the mechanism that you should draw the Lewis dot structure. So we will start with an example, and I will explain that how we can draw the Lewis dot structure. So for example, as we're talking about organic chemistry, and the main and the most famous and abundant um, atom we are most commonly discussing is, and the first thing we discuss in organic chemistry is basically the carbon. So, the carbon belongs to the food tech group in periodic table, and it has the four unpaired electrons in its outermost shell, right? The overall atomic number is a 6, right? And it has the 1s2 and then the 2s and the 2p. These are the electrons which are divided, right? So you know that it goes through the hybridization and in its excited state, but right now we are just discussing its ground state electronic configuration. So it has the four unpaired electron in its outermost shell. So what it is happening that if I will write that one, so this carbon is basically the atom, it's atomic symbol, right? And these dots are basically showing the outermost or the valence electrons. Now I have drawn the single electron because these are the unpaired electrons. So unpaired in a 1s, two in a 2s, and then the 2py x, 2py, and 2pz, right? So that's why it is able to make the four bonds with another one to complete its octet one. So right now we see that the carbon has the four electron in an outermost shell, and according to the octet rule, it must acquire four more electrons to complete its octet one. So what it can do, so it can make the four bonds with the different atoms, or maybe it is getting making that four bonds with the hydrogen, maybe with some with the carbon, oxygen, nitrogen, sulfur, or any other atom, depending on that what is in its vicinity and with which it is reacting, right? So the next thing is we are taking the simplest example, and that is the methane. This is a CH4, right? And you can see that if the carbon is sharing its one electron and it is taking the share from the hydrogen also, which is having the one unpaired electron in its outermost shell, right? And they are sharing these electron pair with each other. And here you can see, so for the hydrogen, I have shown that in a blue, and for the carbon, I have shown that in the black, just to give you the clear idea that you can see that which electron is contributed by which atom, right? So now in the Lewis dot structure, what we do is that what are the bonding electrons? Right now, these are the bonding electrons because this electron and this electron, they are shared by both of these atoms and they are responsible to form a new covalent bond. And that is called the bonding electrons. So the electrons which are involved in a bonding, either the sigma, either the pi, so they are called the bonding electrons. So for the bonding electrons, we either can write in the dot form or we can draw the line because right now they have formed the bond. So for the convenience and to differentiate between the lone pairs, non-bonding electron pairs, and the bonding electrons, what we do is that the electrons which are involved in a bonding, we draw the line. So one line means that there is a pair of electrons, right? So I hope you get that one. So that's why most of you may have heard from your instructor that when we are drawing a line, so there is basically the presence of an electron pair. So one electron has shared with from the hydrogen, and the one electron is shared from with the carbon, right? So next is that how what are the key points and what are the step by step strategy to draw the Lewis structure nicely, and you can understand the concept of this one. So I will share with you some of the important points or the steps that you should follow, and then there is no point that you are not getting familiar with drawing the Lewis structure. So that will be simplified for you, and you will be um, good enough to draw the Lewis structure of any of the organic compound. So the very first thing I want your attention is that you should see that table, which is the Lewis dot structure for elements 1 to 18, right? So from the 1A group, there is a hydrogen, and it's the ideal and its neighbor Nobel gas is the helium, for which it is acquiring the same configuration after getting the one more electron from the carbon, which you have which you have seen in the previous slide. So in a first A group, there is a lithium, there is a sodium, right? So they both have the one electron in the outermost shell. So do remember we are talking about the outermost shell because otherwise their atomic number is different. They have the different number of protons and electrons overall, but we are concerned about what they have in the outermost shell. Why? Because the outermost shell electrons are basically responsible for all kind of bondings and the chemical reactions. Now, the second A group is the beryllium, and they have the two electron pair in their outermost shell, magnesium. Then there is a 3A group, there is a boron, there is aluminium. Fourth group, as we just discussed, is a carbon. Then there was a silicon. Then the fifth A is a nitrogen, phosphorus. 6A is an oxygen, sulfur. Seventh A group is fluorine and chlorine. And the eighth A, helium, neon, and argon. So it means that all of these the third row elements are basically looking the electronic configuration of argon, and for the second row elements they are looking for the neon. One important thing if you notice this one, previously when I show you the carbon, I mentioned the carbon with unpaired electrons, right? They were surrounding um, the carbon element symbol, right? And I didn't write it is in a pair form. Why? Because that was in its excited form when it is going through the excited electronic configuration, where from the 2s orbital, one electron jumps to the pz orbital, right? So that's why the four orbitals are having the unpaired electrons, but this is a ground state where it is having the two electron in a 2s and then one electron in a px and one electron in py. I hope you already know this because we have talked about this in our previous lectures. So our example for discussion is the methanol. And if you are given this molecular formula, so the very first thing is that you have to find out that what is the connectivity of that compound, how these atoms has arranged. So I will discuss with you that what are the exceptions, what you have to follow, and what is a step-by-step strategy to drawing the right Lewis structure of any of the organic molecule. Now, the step one is, so I'm just referring you that what example we are following for this is basically this methanol, right? So if you remember, so there are the three elements which are participating here. So there is a carbon, there is an oxygen, and there is the hydrogen. So see, the very first step is the first determine the total number of the valence electron in a molecule. This will be the sum of the group of all atoms plus the charge. I will explain you that we have to include this charge as well if it is carrying any charge. Each atom must have 8 electrons, octet rule, in its outermost shell, and hydrogen is an exception. So, for example, if you just look back to this example, so I haven't mentioned any of the charge, either the positive and the negative. That means this molecule is the neutral one. And we can even the cross check by drawing the Lewis structure. And if instructor is interested that and he or she ask you for identifying the charge on each atom, so you should know how to calculate that formal charge, and that we will discuss later. So the very first thing is you have to calculate the outermost valence electron for each atom, and then overall we will calculate for the whole molecule. So we know there are the three elements, the three atoms which are present in that molecule: carbon, oxygen, and hydrogen. So there are the four hydrogens in total, and each hydrogen has the one valence electron. So what is the overall contribution of the hydrogen is the four. Oxygen has the six electron in its outermost shell. I can refer to this. You can see 2 to 4 and 5 and 6, right? And for the carbon, it has the 4. So 4, 6, 4, we got this 14 total valence electron of the molecule. That is the first step. Now, why we are calculating this? Because overall at the end, we have to satisfy this, that either that is fulfilling and satisfying the total number of the valence electrons which we have calculated for the molecule. Now, the step 2 is, and for step 2, I'm referring this example. This is NO3 negative, right? And now this is a different example than the methanol, because methanol was a neutral. And here the NO3 is basically in an ionic form, and this is carrying the negative charge, right? This is basically anion. Now the second step is draw a skeletal structure for the molecule which connect all the atoms using only single bonds. So the first effort is this one, that you will, from this molecular formula or the condensed formula, you will basically draw the open structure in a way that firstly you will allocate the single bond, right? The central atom will be the one that can form the greatest number of the bonds. So we cannot keep the oxygen in the center, because the maximum limit of the oxygen to make bond is the 2, while the nitrogen can make the 3 bond, right? So you remember in the two ways that you have to keep that element or atom in a center which is having the low electronegativity than the other atom, right? Which has a lower electronegativity, or which is on the right side of the periodic table, or which is basically which is able to make the more bonds, right? So if we compare the electronegativity of these ones, so these are the nitrogen uh, has the low electronegativity as compared to the oxygen, or you can remember that the nitrogen comes belongs to the fifth group, and the oxygen from the sixth group. So here you can see on the more right side than the oxygen, the nitrogen do exist in a periodic table. So you have to draw the nitrogen in the center, and then you will make the single bond with the numbers of the atoms have given to you. So here we have the 3 oxygen, and we know the nitrogen can make the 3 bonds. So we can allocate each oxygen to the nitrogen on each side, right? So here you can see in the previous case, we draw the carbon in the center, right? And then this was linked with oxygen, and the hydrogen will always kept on the terminal side or outer side. Why? Because the hydrogen is only able to make the single bond. So that's why the hydrogen has its own exclusivity and its exception. So you always draw the hydrogen on the outer side. So here in drawing Lewis structure, hydrogen will always be drawn at terminal, as it can make only one bond. So here we have to firstly calculate the overall valence electron of the molecule. So nitrogen has the 5 valence electron in its outermost shell. Oxygen, each oxygen carries the 6 electron in its outermost shell, and here overall we have the 3 oxygens. So total we have 18, right? What is the charge on it? So the charge is a negative, so we will take it as a 1, right? and the total valence electrons are the 24. Now we see either in the final Lewis structure, are we satisfying this total number of valence electron? So the first thing is you have to draw, firstly, you have to open up the structure and you have to draw the single bond. Then the step 3 is now we will add the lone pair of electrons. Out of the 24 valence electrons available in NO, 6 were used to make the skeletal structure. How? Because each line means there is a pair of electron, right? And we are counting this as a total molecule valence electron. So there is a 2, there is a 4, there is a 6, right? So 6 electrons are basically in the skeletal structure and in making a bond. Now we will add what the atoms have lone pair, or if they don't have the lone pair, so obviously then we are not able to draw that lone pair. So, but in case of the oxygen, we know they have the two lone pair in their ground state, and there is a one unpaired electron. But we will complete its octet, and to show that when the oxygen's octet will be completed, so we have to draw its extra electron also, which it has to carry, or it has to borrow from making another bond, right? So I can differentiate that for you with another color. So, or I can encircle this one. So you can see that this is the electron, which it is not having in its ground state. But we are mentioning this because we have to write the electron pairs with what the total number of valence electron will be if they are completing their octet one, right? So here you can see originally the oxygen has a two lone pair and one unpaired electron in their outermost shell, and we have drawn and this electron also, because after getting this electron, this oxygen will able to complete its octet one. Now the step 4, if there are remaining electrons, they can be used to complete the octet of the central atom. If you have run out of electron, you are required to use lone pair of electrons from a terminal atom to complete the octet on the central atom by forming multiple bonds, right? Bond or bonds. In this case, N is short 2 electron, so we can use a lone pair from the leftmost oxygen atom to form a double bond and complete the octet on the N atom. Now, this is not possible for every kind of atom. You have to see that what is the valency, what is the capacity of an atom to form the bond. So as we know that the oxygen is able to make the two bonds, so it still have the possibility and capacity to make another bond. Now for the nitrogen, we know originally that the nitrogen also have a lone pair of electrons, right? So it means that can take back that lone pair, and it will acquire and it can make an extra bond with that oxygen. So here you can see that for this we will locate this electron pair to the nitrogen, and there is a double bond, the multiple bond which has formed between the nitrogen and an oxygen, right? So the bonding electron will be shown by the single line, non-bonded electrons as dot pair, and the unpaired electrons as a radical or the single electron pair, right? And if you just see this one, now this oxygen turns to have the two lone pairs and two bonds with the nitrogen, right? One is a sigma, another one is a pi bond. Now for, just to mention this, I could write this one for you, that you should know this is the pi and this is the sigma one, right? So here on our next slide, we'll see that the step 5, if the two atoms only share a single pair of electrons, they form a single bond and a single line is drawn between them. If two pairs of electrons are shared between two atoms, they form a double bond or the two lines. If three pairs of electrons are shared between two atoms, they form a triple bond. So for example, if there is the single pair electron which is in a bonding with the two atoms, then there is single. If there are the two pairs, double line, and these are the triple line. And you have seen in the classification of organic compounds that is showing you an example of the alkane, alkene, and alkynes one. Now we'll talk about the formal charge. The formal charge calculation is required for drawing the right structure of the Lewis structure. So Lewis structure is incomplete if you are not allocating the formal charge to the molecule and the atom. So the charge on an atom is in a molecule or polyatomic ion is called its formal charge. To derive a formal charge, write a correct Lewis structure for the molecule or ion, then assign to each atom all its unshared non-bonding electrons and half its shared bonding electrons. Compare this number with the number of valence electrons in the neutral unbonded atoms. So one thing you have to remember is for a neutral unbonded atom, the positive charge on the nucleus equals the number of its surrounding electrons. So when there are more positive charges on the nucleus, then counterbalance negative charge from the surrounding electrons. That atom has a positive formal charge. Conversely, if the number of electrons assigned to a bonded atom is greater than that assigned to the unbonded atom, the atom has a negative formal charge, as we did in the oxygen. And we will see an example with the nitrogen as well, right? Because we allocate the extra electron to complete the octet one. So then by logic, it has to carry the negative charge. So the formal charge calculation formula is the formal charge equal to the number of valence electron in the neutral unbonded atoms, or you can say this is the number of valence electron in their ground state. For example, carbon is carrying the four electron in an outermost shell or the valence electron, so we will write the 4 here. Now minus all unshared electrons, which are the non-bonded or the lone pairs. Then there is the plus 1/2 of all shared electrons, right? So I can simplify more for you in a way, if we can write this way, that you have to write the formal example. We can go for this. Yeah. So the formal charge, sorry. Yeah. Formal charge calculation is equal to valence electrons, right, minus non-bonded, or you can say these are the lone pair, because the lone pairs are which are not non-bonding electrons, which are originally have, but they are not participating first level in the bonding. As for example, you have seen the two lone pairs in an oxygen. Then there is a minus of bonded electrons divided by 2, right? So this is the 1/2 of the electron. Why we're writing the 1/2 is this, because each atom is contributing the 1 electron. So if you write the total number in a line, this is electron pair, but you know that from this electron pair, each electron is contributed by each of the atom, right? So for calculating that particular atom share, we have to divide this one. So we are writing the total number of the bonded electron, and then we are dividing this with the 2 to get the share of one of that atom. So then the fourth point is this, that the sum of all the formal charges is equal to the total charge on the molecule or ion. And we will practice this now, and you will be able to understand this completely. Here, this was a nitrogen, NO3 nitrate we have seen, and we have to calculate its formal charge. So the very first step was that we have to draw its right Lewis structure, right? So the right Lewis structure is this one that we have kept this nitrogen in the center because this is the least electronegative than the oxygen, and it is able to make the more bonds as compared to the oxygen. Then firstly, we allocated the single bond. We write their electron lone pairs of the electrons, and we have seen that what are the total number of the valence electron. Let's count this one. So 2, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, right? And we calculated this that NO3 has the 24 valence electron as a whole in this molecule. So that's satisfied. Now we have to calculate the formal charge of this molecule or polyatomic um, compound. So here you can see, after doing the calculation of the formal charge, we get this nitrogen is carrying the positive one, this oxygen is carrying the negative one, and this oxygen is carrying the negative one, right? That makes sense because this nitrogen was able to make the three bonds by max, and it is making an extra bond. So which is making this a little deficient in the electron because this lone pair was not actually the part of to make a bond. So this is already sharing that one. So that's why it is carrying the positive one. It is deficiency of the electron is always shown as a positivity. So now for the oxygen, we have drawn that this is electron which it has to borrow to complete its octet one, right? And it is still deficient with the one bonding. It can make another bond to complete its octet one. So now, right now, this is not making bond, but this is carrying this electron, which it is required to complete its octet one. So that's why this is getting the negative one, and this is a negative one. So what would be the overall charge on this molecule? So that would be in a case that this plus will be cancelled with this minus or any of the minus, and the overall charge on this NO3 will be minus, right? Which I have drawn initially. Now there is a question that how I have calculated this. So let's see, for one oxygen, if you just look at this one, so oxygen's valence electron formal charge calculation is equal to if, and for each for in a molecule, you have to do the calculation individually for each of the atom, not as a whole a molecule, right? So firstly, we are doing this calculation with the oxygen. Either you can say the number 1, 2, and 3, right? We are doing the calculation with the oxygen 1. So the formal charge calculation, what we have to write is that I have to write the valence electrons minus lone pairs, right? Minus bonded electrons divided by 2, right? So valence electron and oxygen are 6 minus lone pairs, which are the non-bonding electrons on this oxygen, right? So these are the 4. So these are the 4 electron pair, right? So do remember that we don't have to write the pair as a 1. We have to write the total number of electrons in that one. So there are the 4 electrons, but these are the 2 pairs of electrons. So 4 and minus, there's a bonding electron. So bonding electrons are 2 and to 4. So 4 by 2, and that will give you the idea that the oxygen is maybe basically contributing or sharing the 2 electrons. So we will get the oxygen share. So here 6 minus 4, and this is the minus 2. So overall, this is having the 0, right? So this oxygen is not carrying any charge. So this electronically, this is on the 0 charge. Now we can do the calculation for oxygen number 2, right? So for this, you have to see that there is a 6 valence electron minus how many lone pair or the non-bonding electrons there. So here these are 2, 4, and 6. So these are 6 minus bonding electrons are the 2, 2 by 2, right? So this is a 6 minus 6 minus 1. So overall, we have -1 charge, right? And that what we get it, which I have written here. And I have proved from the formal charge calculation. So this oxygen is carrying the negative charge, and same we will do with the 3, and this will give you the same answer, because they both, these both 2 and third oxygen are in the same kind of bonding. So that was for the formal charge calculation. And now the next is your task, which you have to submit. And I'll check that if you are able to get the concept that how to draw the Lewis structure and how to calculate the formal charge. So the question number 1 is that you have to draw the Lewis structure. And of these ions, and show which atom in each bears the formal charge. So there is a CH3 and H3 positive. This is the overall charge on a molecule, and you have to see that which atom is carrying this positive charge, and it is giving the overall molecule the positive charge. This is a carbonate, CO3 -2. This is OH hydroxyl -1. And here the second question is draw the Lewis structure showing all valence electron for these molecules. So you have to draw the dot structures, and you have to calculate what are the total number of the valence electron in each of these one. So this is a C2H6, CS2, and HCN. So that was the overall, and that's your task. You have to submit this one, and I hope you got it, and you can send your queries either under the video, or you can email me if you have any misunderstanding, or you still have the questions from that topic. Have a good day. Thank you so much.